In this lesson, we're going to talk about a few more related rate problems, still using some geometry, but this time not volume or area type problems, but geometry that might involve proportions or Pythagorean theorem. And so in this first example, it says that if we have a man that's 6 feet tall walking away from a 15 foot tall lamp post. So let's go ahead and draw that. We've got a lamp post. I'm not going to really draw it, but anyway, here's our lamp post shining our lights. 15 feet tall. So that's stationary. It's not changing in its height. The man is 6 feet tall, and he's walking away from this thing, so we'll just put him here. So he is 6 feet tall. That's not going to change either. And it says that he's walking at a rate of 1 foot per second. So we are given his, I guess we'll call this x here. So we're given this change in x over time is 1 foot per second. It says, how fast is the length of his shadow increasing? Well, a shadow is created from the light coming down at an angle. So the shadow will be in front of him. So I'm going to give that a different letter. We'll just use Y. So it wants to know how fast the shadow is increasing. How fast is it? So they're asking us to find dy dt. Okay, and then it says how fast is the far tip of the shadow traveling. So here's the deal. How fast is the length of the shadow increasing is going to be dy dt. When it says how fast is the far tip of the shadow traveling, well, that's going to be whatever we get for this rate of change plus his original rate of change combined. So, it'll be both of these, x and y together. All right, so the geometry that we need to use here is probably going to be similar triangles because we've got a right triangle here with this man, the smaller right triangle, and a large right triangle here with this light pole. So we know that in similar triangles we can set up proportions. And so in the big triangle, we would have 15 over the whole bottom of this, x plus y. And in this small triangle, we would have 6 over y. This over the bottom equals the man's height over the bottom. Can't see what I'm writing. So it's just proportions, proportional. Now I know to solve a proportion, I can cross multiply. So I've got 15y equals, and then cross multiply here, I get 6x plus 6y. Well, I'm going to put the x's on one side, y's on the other. So subtract the 6y, I get 9y equals 6x. And I was given one rate of change, correct? I've got two variables, so it looks like I could go ahead and take the derivative. So I have 9 dy dt equals 6 dx dt. And I was given dx dt was 1, so I can plug that in. So I get 9, not d. So 9 dy dt equals 6 times 1. So dy dt equals 6 over 9, or 2/3, and this was in feet per second. So the shadow length is increasing at a rate of 2/3 feet per second. Shadow increases at 2/3 feet per second. All right, but remember they asked a second question, how fast is the far tip traveling? And we said we were going to have to combine the two rates. So remember, his original rate of travel was 1 foot per second. And then we're going to add to that the shadow rate, which in this case was 2/3 feet per second. And so we get a total of 1 2/3 feet per second. So the shadow tip is moving at a rate of 1 2/3 feet per second. All right, in this next example, it says that at a dock, a winch is reeling in a rope at the rate of 2 feet per second. So they're giving us a rate here. The rope is a rate of 2 feet per second. So I guess we'll call that dr dt is given. And it's 2 feet per second. It says the winch is 20 feet above the surface of the water and the rope is attached to a boat. This attachment is at the water's surface. How fast is the boat moving when 22 feet of rope is paid out? So when there's 22 feet of rope left. So let's see if we can draw a picture. So we've got our water surface. We've got this winch, which is probably on the dock, attached to some kind of pole. We'll say this is the dock. Here's our pole. And here's our winch that's pulling in this rope. So it says that it's at the water surface, so it's attached to this boat somewhere at the bottom of the, or at least at the, I have no idea what kind of boat this is, so we'll just make it a cute little boat. All right. So anyway, it's attached to that boat. We're going to pull it in. And as they reel in this rope, they're pulling in the rope this way. And it's pulling the boat in towards this dock or towards the pole. And so it says that we want to find out how fast is the boat moving. So the boat is moving along the water, not along the rope. So we're going to let this be x right here. So we want to find dx dt when there's 22 feet of rope, when r is 22. Now, r is changing, right? So just r is 22 at this point, and we want to figure out everything else. So we can't label this 22. I mean, we know that that's when we're going to find it, but it's just r right now. And so we're assuming that this is a right triangle. So they don't give us anything to compare it to. So in a right triangle, really all we really know about right triangles that we could use here is probably Pythagorean theorem. Now we do know that this winch was 20 feet above the surface of the water. So this thing from here to the water is 20 feet. So I could set up a Pythagorean theorem here that says x squared plus 20 squared would equal r squared. So that gives me some kind of equation or formula to work with. And in this equation or in this formula, I have two variables. I was given one rate of change, so I should be good. So I'm going to go ahead and take the derivative here. So the derivative of x squared would be 2x, but don't forget that we're taking this derivative with respect to time, so we still have to add the dx dt, plus the derivative of 20 squared, or the derivative of 400 is just 0, equals 2r dr dt. All right, so let's plug in what we do know so far. So we know 2, we don't know x, we don't know dx dt, that's what we're supposed to be looking for, so I'm going to leave that in there, equals 2r, r is 22, dr dt is 2. But in order to solve this thing, we've got to fill this spot in as well. So let's go back to our relationship here. This is the overall relationship where R is changing, but we know that at this particular point, R is 22. So what I could do here is just set up a separate equation when R is 22 and solve for X. X squared plus 20 squared equals 22 squared. So X squared plus 400 equals, what is 22 squared? 484. So X squared equals 84. So X is going to equal plus or minus the square root of 84. And 84, we can simplify 242, 221 is 2 square root of 21. So when R is 22, X is 2 square root of 21. All right. So using Pythagorean theorem, we can find out what X is at that same time. So now we've got 4 square root of 21 dx dt equals 2 times 2 is 4 times 22 be 88. We're going to divide by 4 square root of 21. So dx dt equals 22 over square root of 21. Sorry, I forgot. Can you see that? 22 over square root of 21. Now, the boat is being pulled in. So it's being pulled in at a rate of 22 over square root of 21. And this is going to be in feet per second. But if it's being pulled in, that means that it's going backwards. And so this should be negative. And so I should have done this at the very beginning. There's a way that it should have turned out negative, and that's way up here at the top. Because it's being pulled in, this should have been a negative given information. It's being reeled in at 2 feet per second. So it's getting shorter, it's moving to the left, so it should have been negative. And so if I go back and I put in a negative 2 for my dr dt right here, this would be negative 88, which would have given us the negative 22 carried out throughout. And if you divide negative 22 by square root of 21, you get negative 4.801 feet per second if you want a decimal version. So these geometry problems can be any type of geometry problem. This one's Pythagorean theorem. This one was similar triangles. Remember, we also have all of our formulas from geometry. So anything that we can do some kind of comparison in, any kind of formula where you can do a comparison of the rates is applicable, is possible.